So in this session, we're going to be talking about spontaneous rupture with fault friction for both quasi-static and dynamic problems. The concepts we'll cover in this session include setting up those simulations as well as a description of the fault constitutive models and the parameters within those models. We'll cover static friction, slip weakening, and Dietrich-Ruina rate state friction with the aging law. Within the context of fault friction, we will discuss nonlinear solver parameters, absorbing boundaries in dynamic simulations. We'll also discuss time-dependent Dirichlet boundary conditions, as well as initial and time-dependent fault traction perturbations. So first, let's go over the governing equation, revisit the governing equations in the context of fault friction. So here we have our fault with tractions on the two sides of the fault that couple it together, and the relative displacements across the fault correspond to the fault slip. As we discussed on Monday, we have our norm boundary condition, and then when we bring in the fault boundary conditions through the domain decomposition approach, we have Lagrange multipliers. We have Lagrange multiplier on the positive side of the fault for the fault traction. On the negative side of the fault, we have equal and opposite fault traction. And we have our constraint equation for the slip and its relationship to the relative displacement. So in general, in prescribed slip simulations, we're setting what the slip is, and then we need to solve for the relative displacements on each side of the fault, as well as the fault tractions. Now in a fault constitutive model, we have constraints on the fault tractions, and our slip is unknown. As before, in the same way that we represent our displacement field in terms of a sum of linear combination of basis functions, we're doing the same thing for our Lagrange multipliers and fault slip. And so that gives us our integral equations in the weak form for the overall residual. Here's just the portion corresponding to Lagrange multiplier terms. Here's our constraint equation written out in terms of our basis functions. And so those are all those equations are exactly what we had before. Now when we put in our fault constitutive model, we have a limitation on what our shear tractions can be. They must be less than or equal to the tractions coming from the fault constitutive model. Within Pilot, we form all of our fault constitutive models in terms of fault friction. So the friction stress, when we have compressive normal tractions, it's equal to a cohesion minus the coefficient of friction times the normal stress. If we have identically zero normal traction, then it's just equal to the cohesion. In general, in our fault constitutive models, we don't distinguish between fault opening and not fault opening. We enforce conditions related to no penetration and open in the free surface separately outside of the fault constitutive models. That means that the fault constitutive models don't need to worry about whether the fault is opening or interpenetration. All of that is handled consistently without redundant code. And so in order to handle cases where we don't want interpenetration or the fault opens up and we want to enforce a free surface boundary condition on the fault, we have this constraint that the normal traction times the normal displacement is equal to 0. So that means when we're if we have compressive tractions, that means this T normal is less than 0. So that means U normal must be equal to 0. And then if we have U normal greater than 0, then our T normal as well as our T shear components are equal to 0 to enforce a free surface boundary condition. So that are our constraint equations that we want to apply in the context of our fine element formulation. And the solution algorithm we use involves what we call a friction sensitivity solve inside our main nonlinear solve. And what we do is we first perform a nonlinear iteration assuming no additional slip. Then we check to see if our fault constitutive model is satisfied. If it is satisfied, then we don't need to make any adjustments to the solution. And we just keep plugging along. However, if the fault constitutive model is not satisfied, that is, our shear tractions exceed those that are allowable in terms of fault friction, then we want to update our slip estimate so that it's consistent with this reduced traction coming from the fault constitutive model. And to figure out how much slip to impose or increase to reduce the tractions, what we do is we extract a subset of the system associated with just a fault. So here's our A matrix now is just our terms associated with the vertices on each side of the fault. So on the positive side of the fault, we call that N plus. Those are normal degrees of freedom that are associated, sort of conventional degrees of freedom that are associated with the vertices on the positive side of the fault. And when I say positive side of the fault, I mean the vertices that are immediately adjacent to the fault surface. Then we also have the degrees of freedom immediately adjacent on the negative side of the fault surface. Then we have the rotation terms here in terms of capital L. The P refers to these are associated with the Lagrange multipliers, or instead of sort of N degrees of freedom, we have P degrees of freedom associated with the fault. Then these terms, so this is our sort of A matrix extracted just for our fault system, where our unknowns are the displacements immediately adjacent to the positive and negative sides of the fault, as well as our Lagrange multipliers. And then we have our conventional residual terms on the right hand, external forcing terms on the right hand side. And so what we want to do is we want to determine, given a perturbation in our Lagrange multipliers to satisfy our fault condition, we want to compute what the slip is. And so if we extract our equations, we end up with an equation for the vertices on the positive side of the fault, another equation for the vertices on the negative side of the fault, and then an equation relating the perturbation in our displacements to the perturbation in the slip. And so we solve, first we solve this linear system for the positive side of the fault, then we solve this linear system for the other side of the fault, and then we can compute our perturbation in the slip vector that'll give us an estimate of how much slip is required to match our fault constitutive equation. And so once we have that estimate, then we will repeat the process. This converges very quickly if we have our fault embedded in the middle of the domain, so that slip on the fault does not cause deformation throughout the entire domain. In cases where we have a through-going fault that reaches the edges of the domain, then slip on the fault can affect the displacements everywhere in the domain, and are using this equation here to compute our using that linear system to estimate the fault slip becomes a poor approximation, so it takes a lot of nonlinear iterations. And in our discussion of solvers, Matt mentioned things like variational constraint problems or variation inequalities, and that is future work for Pilot, is to reformulate this constraints associated with the fault constitutive models in terms of variational inequalities, so that instead of having this friction sensitivity solve, it becomes part of the whole nonlinear solve, and we end up with a much faster convergence, because instead of updating sort of a portion of the system and then letting it gradually migrate through the rest of the system through the nonlinear solve, we'll be doing a sort of a simultaneously solve for all of the degrees of freedom and updating our tractions and slips simultaneously with the rest of the displacements. So some comments about the friction and nonlinear solver parameters. With our fault constitutive model, we have an additional parameter to be aware of in addition to the PETSI nonlinear and linear solver parameters. There is a zero tolerance for the dynamic fault, and this is associated with the fact that because we're in these quasi-static simulations, we're doing using an iterative solver and there's a convergence tolerance. We need to decide at what value of slip we're going to consider the fault to be locked. And so this zero tolerance means that whenever we have whenever we have slip less than this zero tolerance, we're going to assume that the fault is locked and basically force it to be locked. Whereas when the slip exceeds that, we'll be assuming that the fault constitutive model that we've updated things to allow slip. Now, what this means in terms of our solver parameters is that when we're doing our linear solves within the nonlinear solver, we need to make sure that we're going to converge at a higher tolerance than our zero tolerance for detecting the locked fault and imposing a locked fault. So in order to make that, in order to have the linear solver converge to a value tighter than our zero tolerance, we want to set our relative tolerance to a very small number to force the linear solve to converge due to an absolute tolerance. And we want our absolute tolerance to be generally 1 to 2 orders of magnitude smaller than our zero tolerance. On the other hand, our nonlinear solve will have a lot of trouble trying to converge if it's going after a tolerance that's tighter than the zero tolerance. Because we really can't resolve anything tighter. We can't resolve fault slip, for example, tighter than the zero tolerance. And so we again don't want to use a relative tolerance. We want to be using absolute tolerances with the friction. So we set our relative tolerance to a very small value to force the absolute tolerance to be the one that is used. So it'll hit the absolute tolerance criteria, satisfy our absolute tolerance criteria first. And so we want our nonlinear solve absolute tolerance to be 1 or 2 orders of magnitude larger than our zero tolerance. So we have, in terms of order of magnitude, our absolute tolerance will be 1 to 2 orders of magnitude bigger than our zero tolerance, will be 1 to 2 orders of magnitude bigger than our absolute tolerance. And the absolute value of what those tolerances are in terms of are they 10 to the minus 8, 10 to the minus 10, or 10 to the minus 6, that is going to depend on the resolution that you need to satisfy your constraints and observations. So if you're trying to look at interseismic deformation and slip rates, the order of, in non-dimensional units, say 10 to the minus 6, then you're going to need solver tolerances that are considerably tighter than that. Like say your slip rates, if you're looking at a centimeter per year, you're starting to get down into sort of the 10 to the minus 9 type tolerances in terms of non-dimensional units if you're using kilometers. And so you may need to set up your solver tolerances to be pretty tight. Whereas if you're doing just a static, you want to detect slip, or you're doing sort of a much faster slip rate deformation, then you can get by with larger tolerances. Here's an example of specifying those parameters, and specifically the solver parameters within a .cfg file. So within our faults, we're going to specify a zero tolerance. In this case, I'm specifying a zero tolerance of 10 to the minus 11 in non-dimensional units. If I look, here's my linear solver tolerances. So I've imposed a very small relative tolerance, 10 to the minus 20, so that I'll always hit my absolute tolerance first. Notice that my linear solver absolute tolerance is 1 order of magnitude smaller than my zero tolerance. And my nonlinear solver, again, I use a very small value for my relative tolerance, and then 1 order of magnitude larger than my zero tolerance for my nonlinear solver absolute tolerance. We also can specify the type of solver and preconditioner for our friction sensitivity solve. And so you'll see when we go through our examples that we're going to generally that these are very small, and so we can use we don't need a highly sophisticated solver. We want something that can perform, a number of, say, 10 to 15 iterations as fast as possible on a small system. So the additive Schwartz preconditioner actually does quite well. This value is, the name has been changed. I'm going to make a note of that. We'll look at the .cfg files and we'll see that that name has been changed to its sub-TC AMAT equals 90, I believe. That's true. That's in our updated .cfg files that we've updated since we've done the tutorial, so they'll be present in the next release. There's generally no harm in having that previous. You'll just get a warning that that value has not been used in the solver. So let's talk about fault constitutive models. Here's four of our main fault constitutive models. We have the static friction model. This is what you'd expect, a static coefficient of friction. We have a slip weakening friction model where the friction decreases with slip to a lower limit. This is your sort of classic dynamic static coefficients of friction, but it's slightly regularized in that instead of instantaneously dropping from the dynamic coefficient of friction to the static coefficient of friction, it decreases as slip develops over some length scale. Then there is an equivalent model where that decrease is controlled by a passage of time rather than accumulation of slip. The time weakening is generally only used in special cases in dynamic spontaneous ruptures where you really don't have much control over your slip time histories, and you're just going to try and impose some very basic stabilization of the fault constitutive and that weakening from the dynamic value to the static value. It really has no physical meaning in terms of physics it involves. It's purely a numerical stabilization technique. Rate and state friction, we have the Dietrich-Carina rate and state friction with the aging law. And additionally, we have some less popular fault constitutive models that are combinations of slip weakening and time weakening that are basically the time weakening portion is used for the nucleation of the spontaneous rupture, and these are used in a few SCEC dynamic rupture benchmarks. That's why there are very specific cases that were used in those benchmarks to nucleate in ways that could be used in a research problem, but there are other ways through the initial traction and time-dependent tractions to nucleate that may be simpler to set up. Our static friction model, here's our equation 14, coefficient of friction equals the static coefficient of friction. Some things to note about this particular fault constitutive model in quasi-static problems is that slip continues once the threshold for the shear traction is reached. You will never get stick slip behavior because there's no way to lock the fault up again. You'd actually have to basically decrease your applied tractions through some sort of artificial means to get the fault to lock up again. Generally, it's only for that reason. It's only used in static simulations. So any time stepping is generally not done with a static coefficient of friction. For quasi-static modeling, generally, and dynamic modeling, a very popular friction model is the slip weakening friction. Here, the plot shows the coefficient of friction decreasing from a dynamic value of 0.6 down to a static value of 0.1 as the slip develops up to a value of D0. And so in mathematical terms, that's up here in the first half of equation 15. So we can see is when d equals 0, we end up with our static value. As d approaches d sub 0, we reach our dynamic value, and then when d is greater than d0, we have just our dynamic value. In quasi-static simulations, we'll often want to impose this weakening within a single time step, and so there is a special flag to have that when you proceed to the next time step, to set your the accumulated slip back to 0, so that then you get the fault will lock and you have healing. In dynamic simulations, generally we want this weakening to occur over many time steps, and so what this means is that we don't have this sort of reset or stick slip behavior. The fault generally will remain locked as long as there's it will remain slipping as long and with the coefficient of friction at the dynamic level. The time weakening model has the exact same formulation, only replace as the slip weakening model, only replace the slip with time. So instead of D0, we have T0. This shows the same drop in the coefficient of friction from 0.6 down to 0.1 as time progresses from 0 to T0. Rate and state friction. Here is our version and implementation of rate and state friction with the aging law. There's a popular way to regularize this as the velocity goes to 0. That works quite well when you have sort of a semi-analytical approach, such as boundary interval equations or a dynamic simulation. With our quasi-static simulations and our iterative solver, it doesn't make sense to have the coefficient of friction going to 0 as your slip rate goes to 0. So instead, we use a slightly different regularization where we combine the logarithmic term with the linear term, where this linear term kicks in when our slip rate drops below some threshold that we call V linear. So in terms of, if we look at the coefficient of friction for a given value of the state variable as a function of the logarithm of slip rate, or slip rate on a log scale, here's our V linear threshold. So above that, we have a straight line in logarithmic space. But here we have, this is our deviation where we have just a linear variation in the coefficient of friction with slip rate. And this gives a little more stability when we're trying to detect the slip right at very small slip rates. So usually we're going to set V linear to be just 1 to 2 orders of magnitude greater than our 0 tolerance threshold. So in that case, almost all of the time, except for maybe 1 or 2 time steps right about initiation of slip, we'll be out here in the logarithmic dependence, and it's only when we're right around locking up that we'll be down here at this slight deviation. And so we had a question. Is there an error in the slip weakening equation? The first term on the right-hand side is supposed to be static friction, but not dynamic friction. So let's go back. And so you'll notice that here, if I plug in d equals 0, that this right-hand term, this term right here, will go to 0. And so I have u dynamic plus u static minus u dynamic. When d equals 0, I get the static value with this equation. So this equation looks correct. And then when as d approaches d0, then this term this part right here will go to 0, and I'll be left with just my dynamic coefficient of friction. So it looks correct. So getting back to our rate and state friction, here's the aging law, which says that our state variable, which is has units of time, evolves according to this equation. This is a quite simple equation, but it does. You'll notice it is nonlinear. That the rate of change of this state variable depends on the value of the state variable itself. There's various ways to numerically integrate this. We use a very popular one that's been used by Nadia Pusta, Yoshi Kaneko, and others. And so that's our rate and state friction implementation. And so let's look at the other parameters for our fault cohesive dynamic object for spontaneous rupture. So we switch in prescribed simply have fault cohesive kinematic. In dynamic we have fault cohesive din for dynamic. We have our friction model that we pick one of those models from the previous fault constitutive models that we've discussed. We also have the track perturbation. This is for prescribing any spatial or temporal variation in the tractions applied directly to the fault. So your options for imposing loading on the fault is either to move the boundaries or apply tractions to the boundaries to have that transfer stresses onto the fault due to the deformation, or you can directly apply tractions to impose the loading directly on the fault. In dynamic spontaneous rupture problems, we almost always exclusively use the track perturbation. It's only when we need to have sort of plasticity and sort of our solution depends on the absolute value of stresses that we need to worry about the stresses in the rest of the domain. It's sometimes handy to combine the track perturbation as well as the deforming the boundaries to impose things like tractions consistent with the overburden. You don't have to solve the complete gravity part of gravitational body forces to keep your fault in compression. If you put in the gravitational portion directly in your track perturbation. Solver nonlinear, again, in quasi-static simulations, we need to use a nonlinear solver because our fault constitutive models have this feedback between slip and the tractions. Combining those into a .cfg file, here's what the parameters look like. We have our fault, so we need to change the fault component from the default value of a cohesive kinematic object to a cohesive dynamic object. We impose our friction, give it the, I believe static friction is the default. Here I've set it equal to the static friction, so you pick your whatever friction fault constitutive component, set that equal to the friction. You need to specify what the parameters are for that friction model. So just as with our other boundary conditions, we're going to use our spatial databases. Here I'm using a uniform database because I'm going to impose uniform parameters for my friction coefficient model. So it has a label. I tell it the values, so the friction coefficient and the cohesion. I tell it the values such as the, here's my coefficient of friction, it's unitless, and then my cohesion has units of pascals. My traction perturbation, here I'm going to use a simple database for my traction variations. This is probably due to the fact that I'm going to have some variation in the traction, say for example, as a function of depth consistent with the overburden pressure, or I'm going to impose higher tractions in a particular region to get the fault to nucleate. And so it follows the same